Okay, looks like we are going. One second, let me. Okay, perfect. So we're going to pick up. This is part 3 of the Zinc review. And the review is called, going back up here, The Essential Toxin Impact of Zinc on Human Health. And the reference is in the description down below if you want to read it for yourself. Anyways, forgot how long this was, requiring 3 videos. So, let us begin. The role of zinc in neuronal death. So, a prominent and well-investigated example for the control that zinc exerts on survival on the cellular level is in the brain. So this will now be discussed in more detail as an example of the mechanisms by which zinc can influence cellular survival. So normally, homeostatic mechanisms should prevent zinc from accumulating in the brain to reach toxic concentrations as a result of excess oral ingestion. So normally, remember we were talking about the ZIPs and the ZNTs or the ZRT proteins, which are useful or necessary in many cases to get zinc to go from the extracellular space into the cytosol of the cell. And so this is tightly regulated, and so normally those homeostatic mechanisms should prevent zinc from accumulating in too high of concentrations of the brain cells. However, there are reports of neurological symptoms following zinc intoxication. For example, of a boy who showed lethargy and focal neurological deficits 3 days after he ingested 12 grams of metallic zinc. So remember, this is not... 12 grams is a ridiculous amount of straight-up zinc, and what would probably happen is a lot of that zinc is in the oxide form, especially on the surface of that metal, and then a lot of that will end up dissolving in the stomach acid, and so you can get a huge rush of zinc ions by eating a lot of the metal. Anyways, many studies indicate that zinc acts as a neuromodulator, and this is... So apparently there's a lot of zinc transporters, and zinc homeostasis is important within neurons, like in all other cells. And what is this one? The actions of synaptically released zinc at hippocampal mossy fiber synapses. So apparently there might be the possibility that zinc is one of the ions that gets released or absorbed during synaptic activation. Regardless, continuing. On the other hand, experimental evidence indicates that an endogenous zinc may be a relatively potent, rapidly acting neurotoxin, and to a lesser extent, also a gliotoxin. So the glia are a type of cell in the body, or neuronal cell. So let's look up gliotoxin just to make sure that I'm telling you the right thing. Is a sulfur-containing mycotoxin. Well, this isn't necessarily... Let's go back. So yeah, gliotoxins are a broad range of different things, and for some reason gliotoxin is also referring to this particular chemical, which I would assume be a subset of all gliotoxins. So let me just look through this real quick. Belongs to the class of naturally occurring diketopiperazines. This nitrogen and this nitrogen in this cycle would be considered a piperazine, and so it's a class of naturally occurring piperazines. Oh, immunosuppressive properties that may suppress and cause apoptosis in certain cells of the immune system, so that would be something. So let's look up what a glial cell is. Let's go to this. Oh, I'm wrong. So they're not considered a neuronal cell, but they are a brain cell. Okay, cross that. So glia, um, or okay, this is where we can get a little bit confused. But neuroglia are not neuronal cells, but they are cells of the nervous system. So just whatever. Semantics at this point. Regardless, um, are non-neuronal cells in the central nervous system and the peripheral nervous system that do not produce electrical impulses. They maintain homeostasis and they form myelin. Okay, well, yeah. So here is an example of a neuronal cell right here, and the glia are responsible for producing the myelin sheets, which are here in blue. They're responsible for forming these myelin sheets, which help the electrical signal be conducted across the axons of the neuron. So, and yeah, regardless, maybe I should do a review on the glia as well. But anyways, uh, experimental evidence indicates that endogenous zinc might be a relatively potent, rapidly acting neurotoxin, and to a lesser extent, also a gliotoxin. So zinc might be able to exhibit some toxic effects onto the glia. Okay, so that would be, especially if you have a very large concentration all at once, you might see that effect. Anyways, zinc is stored and released from vesicles in presynaptic terminals of a specific subset of neurons that also release glutamate. Therefore, these neurons are defined as glutinergic, uh, glutamate, and zinc, glucinergic. Okay, neurons. Uh, Continuing, zinc can be released from presynaptic terminals during synaptic transmission, enabling it to enter postsynaptic somata and dendrites of cells through zinc-permeable ion channels. Okay, so what does this tell me? So these vesicles are like little bubbles in a cell that are made out of a cellular membrane, the same type of material that makes the cell membrane. And these vesicles can be loaded up with zinc, and zinc can be stored, or it can be stored and then released from vesicles in the presynaptic terminals of a specific subset of neurons. So somehow, if this cell gets activated in order to release their vesicles, then zinc is going to be released from it, and then that zinc can then therefore play a role in the synapses of the of transducing a signal somehow. Continuing, a zinc can be released from presynaptic terminals during synaptic transmission, enabling it to enter postsynaptic somata and dendrites of cells through zinc-permeable ion channels. So here is the soma, the nucleus, and the dendrites on a cell. And this would be the presynaptic area, and this would be the postsynaptic soma, or the postsynaptic somata. So a signal would start here and then be transferred down this axon, and then possibly, if it gets activated, these will then release a signal. Okay, so these are functioning somewhat like logic gates. Yeah, sorry for taking so long for that. So the presynaptic terminals Okay, so chemical synapses pass information directly from a presynaptic cell to a postsynaptic cell, and therefore asymmetric in structure and function. Okay, the presynaptic axon terminal, or synaptic button, is a specialized area within the axon of the presynaptic cell that contains neurotransmitters. So, okay, this is how we're trying to get to it. So here we have a neuron, right? And the neuron has an axon, and so this is the presynaptic areas, and here's the postsynaptic areas. And this junction is called the synapse. Or I should say, this junction is the synapse. So this is the presynaptic area that has these vesicles, and here's the postsynaptic area, which is sometimes called the soma or sometimes called the somata. But here they're calling it the somata, but I would presume that soma is more vogue to use. There's probably a distinction somewhere, but I would not be able to tell you what that distinction is, because remember, this is not my field. So zinc is being released in these vesicles, much like these neurotransmitter molecules. So zinc can possibly be one of these neurotransmitters, and glutamate would be a different one. And there's a whole laundry list of different types of neurological transmitters. Anyways, zinc can be released from presynaptic terminals during synaptic transmission, and this enables it to enter the postsynaptic somata, or this area. This is the postsynaptic soma or somata. Anyways, these channels include NMDA or N-methyl D-aspartate gated channels, voltage-gated calcium channels, and calcium-permeable AMPA or alpha-amino 3-hydroxy 5-methyl 4-isozatol propionic acid kainate channel. Okay, freaking mouthful right there. Just know that these are different types of what do you call them? Channels that are on the nerve cell that allow the passage of different chemicals from outside or inside of the cell to pass through. That's why they're called channels. So here, I shouldn't go into too much detail. Just know that we have different channels that are on the neurons, and those play a role in either activating or deactivating the neuron. Because remember, they are acting like logic gates, where they take in a bunch of inputs, and then have an output on the end of it, and that output ends up becoming the input of a different neuron. And so you repeat this process over and over again, and that's how you get some form of brain function and neuron function. And then one could argue that's how, what do you call it? Not neurons, but that's how you can get the emergence of brain activity. The emergence of brain activity is the culmination of all of these logic gates or semi-logic gates with these chemicals being either released or inhibited in some way. Anyways, in addition to being sequestered in vesicles of presynaptic terminals in the glutinergic neurons, zinc can also be bound to metallothionein, especially metallothionein 3, in perikarya, as well as being taken up by mitochondria. And I do not know what the perikarya is, so let's look that up just so that we're not stupid. The cell body of the neuron, which contains the nucleus. So this is also the soma. So the soma and the perikaryon, and I believe it's called keri, because keri means nucleus, if I remember correctly. So metallothionein 3 is in the perikarya of the neurons, or at least of some neurons, and as well as being taken up by mitochondria. So mitochondria can also can concentrate the metallothionein within them as well. The metallothionein 3 isoform is found only in the brain, and it is abundant in the glutinergic neurons. So this, if you find a protein that is abundant in any particular cell type, we usually presume, especially if it is in a higher relative concentration, if it's disproportionately higher in a certain cell, we would presume that protein has some function that is specialized for that particular cell. Anyways, Exposure to 300 to 600 micromolar zinc for 15 minutes results in extensive neuronal death in cortical cell culture. And this would be pretty high, but exposure to 300 to 600 micromolar. Okay, so for 15 minutes results in extensive neuronal death in cortical cell culture. Considering that neurons store high amounts of free zinc in their terminals that are released upon depolarization, zinc may play an active role in neuronal injury. Furthermore, membrane depolarization. So, as I said earlier, your cells like to maintain an electrical potential across the cell membrane, and depolarization is when that electrical potential is lost. So, with your normal cells, that's normally pretty bad, but neuron cells, at least, tightly control this depolarization. So it's a natural mechanism that your nerve cells take advantage of in order to propagate signals through them. So let's look up depolarization for nerves. Oh, good. You gotta love Wikipedia. It really helps. So it's a change within the cell during which the cell undergoes a shift in electric charge distribution, resulting in less negative charge inside of the cell. So here you can see there's a membrane potential in millivolts, so it's measured in voltage across the cell membrane, and in nerve cells it's normally at about negative 70 millivolts. And then what happens is if it is given enough signal to go over this threshold, and for this particular neuron it's negative 55 millivolts, then what happens is that causes a cascade of channels and signals, or how do I phrase that? That tells the cell to undergo depolarization, which it moves ions very rapidly from outside of the cell or inside of the cell. How do I phrase that? It moves ions very quickly, and that causes the membrane potential not just to go to zero, but to reverse. And this process is called depolarization. And so it gets depolarized so that the membrane potential is now positive 30 millivolts across the cellular membrane. And then after it reaches that, it then, and I can't verify these numbers, and if these numbers are common to all neurons, I'm sure different neurons probably have different levels. But regardless, goes up to 30 and then repolarizes to go back to its normal state. But when it repolarizes, it first hyperpolarizes and is actually more negative than the original, or than what the nerve was originally. So this is something that helps prevent the nerve from getting reactivated too quickly, because then there's a much bigger difference between here and the negative 55 versus here, which is at negative 70 to negative 55. So this is something that helps prevent a nerve from firing over and over and over again. Okay, so furthermore, membrane depolarization, which is associated with acute brain injury. Furthermore, membrane depolarization, which is associated with acute brain injury, greatly increases the potency of zinc to act as a neurotoxin. So if your brain is injured, apparently zinc can become more toxic in that event. So, yeah. Anyways, these people confirmed that by showing that depolarization with high concentrations of 25 micromolar of potassium media requires just 5-minute exposure to 100 micromolar zinc to kill all neurons in cortical cell culture. So remember here, 300 to 600 micromolar concentration for 15 minutes results in extensive neuronal cell death. But this is much higher than this 100 micromolar zinc, and this 100 micromolar zinc can kill all neurons if those neurons are first depolarized by potassium what's it called? With with this potassium media. So if you have a high concentration of potassium in your media, you can cause a depolarization event for a lot of these neurons. And then in this particular state, it's very easy to kill neurons with zinc. So that this is something that you might want to worry about. Anyway, zinc has been described as a critical component of the excitotoxic cascade occurring after ischemia, seizures, and head trauma. The first study providing evidence that zinc accumulation may play a role in the selective death of dentate hilar neurons after global ischemia in rats was done by these people. Okay, so let me read this. The first study providing evidence that zinc accumulation may play a role in selective death. So these people had made the argument that following neuronal degeneration, so zinc wasn't causing the degeneration, but if the degeneration already happened, then zinc would start to accumulate in those damaged cells, and that accumulation is what what's it called? Might play a role in the final killing of the neuron. So that could be through the apoptotic pathway that we were talking about earlier. They don't really, doesn't seem like they're going into too much detail, but this could be important because that could say zinc might be playing an important role, that might be a necessary role. So you might not want to have damaged neurons in your brain. Your brain might want to decide to basically cut its losses and then kill those neurons. And the method by which it is accomplishing that is by getting zinc into those cells to help convince them to kill themselves. That could be a possible mechanism. I'm not saying that that is the mechanism, but remember, your brain has a lot of redundancy in it, and therefore you can actually, you can lose quite a few neurons and still function properly. In fact, I think some diseases, they actually, like some neurological conditions, they might try to deactivate some areas of the brain in order to help with those neurological conditions. But don't quote me on that. I need to reread that. Anyways, continuing. In the meantime, zinc accumulation in dying or dead neurons has not only been shown in the hippocampal hilar region, but also in all brain regions damaged in global ischemia, such as hippocampal CA1, neocortex, thalamus, and striatum. So these are just parts of the brain. So if you can, but also in all brain regions damaged in global ischemia. So yeah, so you can see zinc accumulation is happening in all dying cells after the damage has already been done. Okay, so this could very well be the mechanism by which your body tries to kill these cells. I mean, they're not saying, maybe not. We'll probably find out later. And in fact, this is already 10 years old, so there might have been already some papers released describing whether or not this is true. Anyways, consistent with the hypothesis that zinc accumulation may lead to neuronal cell death, this event was prevented by the intraventricular injection of zinc chelating agents, calcium EDTA. So EDTA is a very popular chelating agent, and we were talking about chelating agents earlier, but they are compounds that are able to wrap themselves around a particular, usually it's a metal, it's usually a cation, and one of the things that they do is they alter the solubility, or they alter the activity of those metals. And so EDTA is frequently used to bind to metals and make them inactive. And another benefit of it is that it can make those ions more water soluble, which can help with their removal. So calcium EDTA is just one of the salts of EDTA. And so by injecting calcium EDTA, it can bind to the zinc and help remove the zinc from their active form. Anyway, zinc release and accumulation of zinc ions was also observed in rat model of traumatic brain injury, where these people showed that trauma is associated with the loss of zinc from presynaptic boutons and appearance of zinc in injured neurons. Again, neuroprotection occurred by intraventricular administration of a zinc chelator. Interesting. Okay, so what? Let me think about this real quick. Yeah, so it sounds like so this could be an example of a typical defense mechanism that your brain would normally employ, um, probably to get rid of small short-term damage, uh, to prevent that from accumulating. But if you get damage all over the brain or in a large swath of the brain, you probably would want to avoid this zinc accumulation effect, uh, because it would probably be killing too many neurons all at once. So that would make sense to me. And because remember, a lot of diseases and a lot of pathologies are actually just your body, uh, just some dysregulation of what is normally a survival mechanism can actually be harmful if it's dysregulated. So I mean, it's almost philosophical, right? It's your survival mechanisms often can backfire if they are dysregulated. So write that down. Regardless, apparently these people have shown that if you inject a chelator or something that prevents zinc from behaving and acting the way it normally would, you can actually prevent some neuron loss. So yeah, neuroprotection. Okay. So this might actually be one of the reasons why things like green tea have a purported health effect. So for instance, EGCG is able to chelate to zinc, and I read a paper stating that it is able to prevent zinc from exerting its cytotoxic effects on cells. So that might be something that people want to look into: is does EGCG end up reducing brain injury by chelating to zinc? I think that would probably be a good study. In fact, I could probably, you know what, I'll look it up right now at Scholar. So let's look up EGCG zinc neurotoxicity. Okay. So rapid communication, attenuation of methamphetamine-induced neurotoxicity in copper, seeing not. So, for instance, here, EGCG protects HT22 cells against glutamate-induced oxidative stress. So it could be the oxidative stress is what is convincing the cell to consume or import more zinc from solution. What else is possible? Anti-amyloidogenic of the green tea extract, EGCG, towards metal-associated amyloid beta species. Ooh, this looks good. I'll probably read that later. Protection against methamphetamine-induced striatal apoptosis by so apparently frequently we use things like methamphetamine to see how to basically cause neuronal cell death in cell cultures, and then we can test the efficacy of different pharmaceuticals or different chemicals at either making that effect worse or better. So here it seems that epigallocatechin gallate, or EGCG, is able to help prevent that from happening. Now here it sounds like they're chalking it up to the superoxide dismutase, which, remember, zinc and copper play a role in superoxide dismutase regulation. So that would be one way to reduce the oxidative stress that is caused by the methamphetamine. That is true. It's also possible that it plays a role in the zinc in the zinc toxicity in of itself. So yeah, I'll probably read those later, but we should keep on going for now. It's 24 minutes. So although zinc is redox inactive in biological systems and exists only as a bivalent cation, there's evidence that zinc toxicity in neurons is mediated mainly by oxidative stress. So, going back to that oxidative stress. So zinc-induced cell death is associated with increased levels of reactive oxygen species in neurons. So zinc-induced cell death is associated with the reactive oxygen species. So just keep that in mind. So, for instance, zinc entry produces oxidative neuronal necrosis in cortical cell cultures. In addition, free radical generating enzymes like NADPH oxidase are induced and activated by exposure to zinc. So NADPH oxidase is an enzyme that is induced and activated by exposure to zinc. So that's very fascinating. So finally, zinc-induced cell death has been shown to be attenuated by various antioxidant interventions. So, yeah, well, that's good to know. So remember, there used to be a lot more hype about antioxidants. I haven't heard nearly as much of it these last few years, but and that's probably because when we talk about antioxidants, we're normally referring, when we do the studies on them, or a lot of these studies, we're usually talking about acute free radical damage and acute high dosages of whatever that chemical that is causing that damage is. So as far as your day-to-day life, the antioxidant concentrations that you consume, so the antioxidant amounts that you consume, that is harder. It is harder to know how it translates from in vitro, these in vitro studies, into in vivo or in life studies. So that is, there's too many papers to go over, but I guess I can go over some of those papers to try to make sense of that a little bit better. So one of the issues is some antioxidants can actually be pro-oxidant if they are in too high of a concentration. I think vitamin C is one of the big ones for that. But, sometimes maybe, especially for acute injury, taking an acute amount of an antioxidant might be very beneficial for at least dampening the damage. Regardless, we should keep on going. So finally, besides oxidative stress, nitrosative stress can also affect zinc-induced neuronal injury. So nitric monoxide plays a crucial role in zinc toxicity by releasing zinc ions from metallothionein. So these the NO molecules, the nitric monoxide, well, no, it's multiple nitrogens. I'm going to look this up just to make sure I have the right one. I feel like a lot of these chemicals have different names, so I just need to... So internet has actually been very bad recently, especially over the weekend. There's way too many people on the internet right now. Yeah, so it is NO. So it must be nitrous oxide. So yeah, NO. Oops. So nitric monoxide plays a crucial role in zinc toxicity by releasing zinc ions from metallothionein. So these NO molecules will bind to, I presume, the zinc, and then allow that zinc to be released from the sulfur groups of the metallothioneins. And inhibition of nitric oxide synthase significantly reduces zinc release from brain slices during oxygen and glucose deprivation. Okay, so consistent with this, Fredrickson and colleagues observed that nitric oxide also rapidly releases zinc from presynaptic terminals. Interesting. So nitric oxide is, if it's released, it is causing the release of zinc from these vesicles in the neurons, and so that can propagate a signal down to the next neuron. That's very fascinating. In addition to the impact of zinc on apoptosis discussed above, zinc-induced apoptosis in neurons might be based on two additional mechanisms. First, zinc-exposed neurons show an induction of neurotropin receptor P75 NTR and P75 NTR underscore associated death executor, or NADE, a combination that can trigger capsase activation and apoptosis. So if you expose the neurons to zinc, it can cause the induction or the production of this receptor, P75 NTR and P75 NTR underscore, associated death executor, so NADE. So both of these, if they are induced, can cause capsase activation. And so remember, the capsases were proteases that can activate each other. So once you get that ball rolling after you reach critical mass, they end up really activating each other and causing the cell to kill itself. So second, high intracellular zinc concentrations trigger dysfunction of neuronal mitochondria, resulting in the release of pro-apoptotic proteins such as cytochrome C, which is something that we spoke about earlier, and apoptosis-inducing factor, or AIF. So, yeah, so basically, the zinc can help stimulate apoptosis or programmed cell death in normal cells, and especially cancer cells, especially in cultured cancer cells. It seemed that zinc could play a very, very active role in causing programmed cell death. But here in neurons, apparently they have the P75 NTR and the P75 NTR associated death executor, which seems to be an additional way that zinc can cause cell death. So if you undergo cell toxicity or zinc toxicity, you're probably also going to have not only your own cells undergoing apoptosis when you don't want it to happen, but your neurons will probably be disproportionately affected. Anyway, second, oh yeah, I already read that. So although the release of intracellular zinc triggers neuronal apoptosis, indicators of necrosis such as cell body swelling and destruction of intracellular organelles have also been observed. So indicating that zinc-induced neuronal cell death might encompass both apoptotic and necrotic mechanisms. So apoptosis is programmed cell death, but necrosis is not programmed cell death. So that is something that this happens to the cell against its own will. Taken together, alterations of neuronal zinc homeostasis have a profound influence on cellular survival during acute insults, or impulse insults, and zinc chelators are discussed as a potential therapeutic agent for the treatment of stroke. So it could be if you have a stroke, if you want to help minimize the cell death that is associated with that stroke, keep those neurons alive, as much of those neurons alive as possible, perhaps using zinc chelators, which help suppress the effects of zinc during that time, could be a therapeutic agent, or could be something that could benefit the person who had that stroke happen to them. Anyways, it seems likely that zinc is also involved in neurodegenerative disease. For example, zinc and deregulated zinc homeostasis could be important to onset progression of Alzheimer's disease. Here the use of metal chelators such as cleophonol to restore normal neuronal zinc homeostasis has shown promising results in vivo. Oh, okay, so if we're talking about people with Alzheimer's with dysregulated zinc, apparently zinc chelators, yeah, zinc and physiology and pathology in the central nervous system. So yeah, it could be that these zinc chelators can play a good role at preventing the progression of zinc progressing injury, zinc stimulating injury. Okay. Anyway, zinc deficiency. As discussed above, systemic zinc toxicity is not a major health problem. On the other hand, due to its essentiality, a lack of this trace element leads to far more severe and widespread problems. Both nutritional and inherited zinc deficiency generate similar symptoms, and clinical zinc deficiency causes a spectrum from mild and marginal effects up to symptoms of severe nature. So, figure 2 had it, so that was all the way up here. So here you can see zinc excess causing these problems, but here zinc deficiency is causing other problems, and these problems are much more prevalent and severe in society. So things such as decreased nerve conduction, neuropsychiatric disorders, neurosensory disorders, mental lethargy, thymic atrophy, skin lesions, decreased wound healing, acrodermatitis, infertility, retarded genital development, and hypogonadism. So yeah, none of those. And systemic symptoms would be growth retardation and immune dysfunction and infection. So, coming down here, human zinc deficiency was first reported in 1961 when Iranian males were diagnosed with symptoms including growth retardation, hypogonadism, skin abnormalities, and mental lethargy attributed to nutritional zinc deficiency. Later, studies with some Egyptian patients showed remarkably similar clinical features. Additional studies in the ongoing years manifested zinc deficiency as a potentially widespread problem in developing as well as industrial nations. Severe zinc deficiency can be either inherited or acquired. The most severe of the inherited forms is acrodermatitis enteropathica, a rare autosomal recessive metabolic disorder resulting from a mutation on the intestinal ZIP4 transporter. So remember, the ZIPs are the zinc importing proteins on the cell membrane. And so the ZIP4 is one of them that exists in the intestines and plays an important role in getting the zinc from your food into the body. And so there's a rare autosomal recessive metabolic disorder where it is much more difficult to absorb zinc from your diet because you are lacking this transporter. Anyway, symptoms of this condition include skin lesions, alopecia, I never can pronounce that right, diarrhea, neurophysiological disturbances, weight loss, reduced immune function, as well as hypogonadism in men, and can be lethal in absence of treatment. So, well, that's interesting. I wonder, so if there was, say, a subset, a group of people, maybe they don't have the acrodermatitis enteropathica. Maybe, so remember, this is a autosomal recessive metabolic disorder. So both of your parents would have to have this gene, and you would have to inherit both of those genes in order to experience acrodermatitis enteropathica. Yo, I can edit it out. So it is possible that there could be large groups of people that maybe they don't have both of the alleles, but they have one, and that might therefore predispose them to higher levels of, or I should say lower levels of zinc, and be in a higher, or have a higher risk factor of having depleted levels of zinc in their body. So that might be something that people want to look at when it comes to severity of disease. When it comes to, yeah, so severity of disease could possibly be increased if these people have low zinc concentrations in their blood normally. And this isn't just for zinc. You have transporters for pretty much every ion, every different metal that is used as a nutrient. So if anyone has any genetic disorder that prevents those transporters from working properly, maybe they work too good or they don't work good enough, they could be in a particular high risk group. Okay, so well, that's interesting because this is telling me that groups with high levels of acrodermatitis enteropathica will also have high levels of carriers as well. And perhaps the carriers are a high risk group for a disease that takes advantage of zinc deficiency. So let's look up distribution. History and physical. Let's look up country. Okay, so not here. What I will want to do is let us by country. There's a lot of dead space in this video, so I'm sorry about that, but what you can do is you can use the arrows to skip ahead if you want. Okay, so let's look up Wikipedia. So maybe that can give us a. So remember, it is recessive, so only one. You need both parents to be carriers, and only 1 out of 4, if both are just carriers, only 1 out of 4 will get both recessive genes on average. So let us see. Yeah, it looks like I won't be able to find a distribution in the world as far as what countries have higher rates of acrodermatitis of this acrodermatitis enteropathica. Regardless, let's continue, because just knowing that would tell me if that country or if that area had higher levels of this genetic predisposition, they might be more susceptible to certain viral illnesses. So, especially viral illnesses that might be prevented or at least alleviated by zinc supplementation. So, let's continue. So, acquired severe zinc deficiency has been observed in patients receiving total parental nutrition without supplementation of zinc, following excessive alcohol ingestion, severe malabsorption, and iatrogenic. Don't know what that means. Relating to illness caused by medical examination or treatment. So it's like a catch-22. Sometimes the treatment is also a cause of pathology. So causes such as treatment with histidine or penicillamine. The symptoms are mostly similar to those arising during acrodermatitis enteropathica. Okay. Yeah. So some reports indicate the existence of another group of inherited disorders of zinc metabolism. They lead to baseline zinc plasma levels above 300 micrograms per 100 milliliters, more than 3 times the physiological level, while iron and copper levels stayed normal. So remember, zinc plasma levels, that is not your cellular level. The cellular level would require the transporters to work properly. The zips should work properly. Okay, but if those don't work properly, um, let's say the zip of your intestine works well, so then your body's able to get plenty of zinc in the plasma. But if none of that zinc can go from the plasma into the cells, or if it can only get into a limited number of cells, then that would be a cause for concern. So, even though this exceeds the normal amount normally found in serum after zinc intoxication, symptoms range from none to severe anemia, growth failure, and systemic inflammation, and resemble zinc deficiency rather than chronic or acute intoxication. So remember, what causes a lot of the damage from intoxication is not from the zinc being in the serum. It's not from the zinc being in the extracellular space. It is from the zinc absorbing into or getting into the cells at way too high of a concentration. So there are some people that that have a screwed up metabolism, and this screwed up metabolism prevents the zinc from getting into the cell. So their plasma, their serum has really high concentrations of zinc, but it's not doing what it's supposed to. In fact, there is either no symptoms, so even if it's really high in the serum, maybe it's somewhat okay within the cell, or you can have symptoms of deficiency, even though the zinc's there. So to me, what this would indicate is someone with this particular deficiency might really benefit from a zinc ionophore in their diet or as a prescription. So if I found out I was one of these people, I would probably start drinking a lot more green tea, knowing that green tea helps zinc go from the extracellular space into the intercellular space. Anyways, the elevated zinc levels have been attributed to excessive binding of serum proteins, for example, by albumin, or to the overexpression of zinc binding S100 protein calprotectin. Yeah, these are okay. So maybe I was speaking a little bit too early. So they're saying here it's not necessarily the transporters that are screwed up, but there are some proteins that are used that the body creates to sequester metal ions, and if it makes too many of these sequestering agents, then a lot of the zinc can be rendered useless, and it stays in the plasma rather than going into the cells where it belongs. So yeah, so if for some reason the albumin binds too well, maybe there's a mutation which makes albumin bind way too good in the plasma, and yeah, so it sounds like perhaps mutations in albumin expression or the type of albumin, if there's a specific mutation in some of the metal binding sites of albumin, then that can cause zinc to not get into the cell the way it should, or the zinc binding S100 protein. So if you make too much of this, that could also cause zinc to not get into the cell properly. Hence, the large amounts of zinc in the serum of these patients are sequestered by proteins, potentially even depleting biologically available zinc. So one would argue then maybe oversupplementation of zinc might be important, or the production of or the introduction of zinc chelating compounds might allow the zinc to be liberated from those proteins in the plasma, and thereby helping the zinc get into the cell where it can exert its biological function. Okay, I mean that might be that might be the direction that a physician would go. Anyways, clinical manifestations of moderate zinc deficiency are mainly found in patients with low dietary zinc intake, alcohol abuse, malabsorption, chronic renal disease, and chronic debilitation. Symptoms include growth retardation in growing children and adolescents, hypogonadism in men, skin changes, poor appetite, mental lethargy, delayed wound healing, taste abnormalities, abnormal dark adaptation, and energy. What is I'm gonna look that up. Is that when your skin gets too dark? As frauds meet. Oh, I see. So this is no. This is of the eyes. So when you're so it might have something to do with the rods of the retina. So dark adaptation reduces coupling, decreases sensitivity of horizontal cells. Oh God. Okay. I don't understand any of that. I just know that it has something to do with the way that the eyes work, especially going into dark areas. Perhaps there are some biochemical changes that allow you to see better at night. And if that could be, there could be some abnormal dark adaptation going on, given zinc deficiency, or given a mutation that causes disproportional um, that causes zinc to not be processed or moved the way it normally would have been. Anyways, moderate zinc deficiency can also occur as a consequence of sickle cell disease. So hyperzincuria, or a lot of zinc in the blood, and high protein turnover due to increased hemolysis lead to moderate zinc deficiency in these patients, which causes clinical manifestations typical for zinc deficiency, such as growth retardation and all these other disorders connected with thymic atrophy. In mild cases of zinc deficiency, slight weight loss, oligospermia, and hyperammonemia, so too much ammonium in the blood. And so I'm going to look up oligospermia because I'm not sure. Okay, just low sperm count. So low sperm count and too much ammonium in the blood. One population in which mild zinc deficiency occurs with high prevalence, even in industrialized countries, are the elderly. So the elderly usually have zinc deficiency, and it's high prevalence. So even in industrialized countries, the elderly have high prevalence of zinc deficiency. So that's good to know that old people normally are deficient in zinc. So here, a significant proportion has reduced zinc levels, and zinc supplementation studies indicate that this deficiency contributes significantly to increased susceptibility to infectious diseases. Yeah, so good to know. I'm going to look that up. I have way too many papers. If you could see, I always cut it out, but I always have a crap ton of tabs open, and then I tell myself that I'm going to get to all of them, and I never do. So my life just becomes, the to-do list gets progressively longer and longer, and it really is impossible to keep up. Anyways, the overall frequency of zinc deficiency worldwide is expected to be higher than 20%. In developing countries, it may affect more than 2 billion people. Furthermore, it has been estimated that only 42.5% of the elderly in the United States have adequate zinc intake. This widespread occurrence, combined with a variety of clinical manifestations, makes zinc deficiency a serious nutritional problem, which has far greater impact on human health than the relatively infrequent intoxication with zinc. Interesting. So, conclusions. Zinc is an essential trace element, and the human body has efficient mechanisms both on systemic and cellular levels to maintain homeostasis over a broad exposure range. So consequently, zinc has a rather low toxicity and a severe impact on human health by intoxication with zinc is a relatively rare event. So nevertheless, on the cellular level, zinc impacts survival and may be a crucial regulator of apoptosis as well as neuronal death following brain injury. So although these effects seem to be unresponsive to nutritional supplementation with zinc, future research may allow influencing these processes via substances that alter zinc homeostasis instead of directly giving zinc. So whereas there are only anecdotal reports of severe zinc intoxication, zinc deficiency is a condition with broad occurrence and potentially profound impact. Here, the application of negative zinc, for example, substances or conditions that deplete the body of zinc, constitute a major health risk. The impact ranges from mild zinc deficiency, which can aggravate infections by impairing the immune defense, up to severe cases in which symptoms are obvious and cause reduced life expectancy. So there we go. Wonderful. So, yeah, I really don't know what to say. That was pretty much, I guess, in conclusion for this video series. Just know that zinc isn't the only metal that your body needs to function properly. Okay, your body needs zinc, it needs iron, it needs copper, it needs selenium, it needs magnesium, calcium, sodium, potassium. It needs all these metals, and all these metals fit their niche, right? And if any one of them becomes dysregulated, it can cause pathology of some sort. So, how do I phrase that? So, when it comes to zinc, though, it seems as though that there is currently a general deficiency among large swaths of the population that needs to be addressed. So I think that it is important to go over how zinc can exert its functions. That way, we can gain a better understanding of how to regulate it and have a healthier relationship with it in order to improve our own health. Okay, so remember, it's not zinc is toxic or zinc is always healthy and therefore we should avoid it or go all in for it. We need to understand the mechanisms by which zinc exerts its role in the body. And therefore, we can start mitigating the negative effects of zinc while maximizing the positives. So remember, for instance, chelating agents were able to suppress zinc's negative effects, especially the acute negative effects, right? And then also, zinc ionophores are also chelators that can affect zinc function, so those can also be benefiting people to help prevent zinc from exerting its toxic effects. So what else should I say? And then going over how zinc can both cause cellular injury or prevent cellular injury depending on its concentration, depending on whether or not the cell was already injured. So this is, I guess that is something that I want to bring up as well. So remember, the neurons, if they were injured, if they were depolarized, or if they showed signs of injury, it seems as though zinc, if it accumulates into those cells, it can convince those cells to undergo apoptosis. It can convince the cells to kill themselves. right? And this reminds me of the cell cultures where we do experiments on zinc concentration on these cell cultures. It seems as though zinc causes more cancer cell lines to undergo apoptosis, whereas a healthy cell line, such as a white blood cell line, which we are able to culture in a test tube, it seems as though it doesn't have the same apoptotic effects on those cell cultures. The healthy cell cultures seem to live better, whereas damaged cell cultures or damaged tissues seem to start to die. So what does this tell me? It tells me that zinc is probably playing a role in drawing a line in the sand of saying if a cell should kill itself or if a cell should stay alive. And it's probably, to me, it sounds like a cancer cell probably exhibits a lot of signals that say it's damaged, it needs to die, but the cancer cell has overridden, or at least partially overridden, those signals. And zinc is, if it comes in at high concentrations, it comes in, draws a line in the sand, and says, you need to kill yourself because you have all these signals and you are just ignoring those signals, or you're undervaluing those signals. And zinc comes along and it changes the threshold of those signals, and then all of a sudden the cancer cell then decides, okay, you are right, I really need to end up undergoing cellular apoptosis. So whereas a healthy cell would have very low of those signals, and as a result, zinc would, even though zinc redefines the drawing of the threshold, that threshold is still miles away from what the cell is actually screaming, and therefore the cell continues to live. So, yeah, I think that's interesting. I think I'll go over that a little bit, read over papers about that a little bit to try to gain a little bit more understanding. But yeah, I think this is a good place to end. So if there are any comments or questions, go ahead and leave them down in the description, and I'll try to get to them, or leave them down in the comments, and I'll try to get to them later. So thanks for watching.